When you're doing a problem that involves significant figures and there are multiple steps in the problem, when you switch between addition and subtraction and multiplication and division, you have to take into account the rule for that particular section of the problem before you can continue on. For example, if you do an experiment and you determine that the density of aluminum, let's say, is 3.62 grams per milliliter. And then you look up the actual density of aluminum. So this is from your experiment. And then you look up the actual density of aluminum is 2.70 grams per milliliter. Okay, and what we would like to do now is we'd like to know, well, how far off are we? What percentage-wise, how far off are we from what we were supposed to get? So again, this is what we got in our experiment. This is the actual aluminum density. So the first thing that we do to figure that out is we're going to calculate what's called the percent error. Okay, so it's the percent error, which is just a measure of how off you are. So the best percent error you can get is 0. A bad percent error would be like 75% or 100%. A big number is bad. The smaller your percent error, the better. So the first thing we do to calculate the percent error is we look at our two numbers. So I've got my 3.62 here. I've got my 2.70. The first thing that we do is we subtract those two numbers. Okay, and the easiest way to do this is always just take the big number minus the small number. Whichever number is bigger, put that number first. So to calculate percent error, we're going to take 3.62 and we're going to, let's make this full screen just to give us some more space, 3.62 minus 2.70. So you might need a calculator for that. So I'm going to just type that in my calculator exactly how I see it on my screen. 3.62 minus 2.70, and I get 0.92. So the first part of percent error is always just to subtract the big number minus the small number. Then your result, the 0.92 in this case, we're going to take that number, so I'm going to scroll down here a little bit more, 0.92, and then here's the only part where you have to decide which number to use, because we're going to divide. Now, if you think about it, this experimental, depending on who's doing the experiment, that number is going to change. If one group is doing the experiment and another group is doing the same experiment, it's very likely that you're going to get two different answers. But this number, the actual value of the density of aluminum, doesn't ever change. The density of aluminum is 2.7 grams. So what I'm trying to tell you here is the number that goes on the bottom is always the actual number. So I'm going to take 0.92, I'm going to divide by 2.70. And, then to make sure that I do that correctly, I'm going to multiply by 100 to get it to a percent. So 0.92 divided by 2.70 equals, and then I times it by 100 to get an answer. Now my calculator answer says 34.074 blah, blah, blah. Okay, now here's where the significant figure rules come into play. Because a lot of times when you do a problem with significant figures, you simply look at the numbers that you start with and you go, oh, well, this number has 3 significant figures. This number has 3 significant figures. So therefore my answer must have 3 significant figures. For the most part, that works just fine. If that were the case, then I could write my answer as 34.1%, and then I would be done. Okay. However, in this case, what's happening is you are subtracting in the first step, and then you're dividing in the second step. And remember, there's 2 different sets of rules. For addition and subtraction, we're just looking at the digits that come after the decimal point. But with multiplication and division, we're looking at the whole number that we're dividing. So when I took 3.62 and I subtracted 2.70, when I got that answer, I looked, and I didn't say anything then, but now I'm explaining that to you. I looked and I thought, this has 2 numbers after the decimal point. This has 2 numbers after the decimal point. Therefore, so does my answer. And the only reason I looked at that now is because I knew I was switching rules from the plus minus rules to the multiplication division rules. Because now that I'm down here and now I'm dividing, the 0.92 by 2.70, now I have to look and go, oh, this number only has 2 digits, 2 significant figures. And so therefore my answer, even though this one has 3, remember your answer can only be as good as your worst measurement. Well, now that's my worst one. So this only has 2 significant figures. This is a conversion factor, so we don't use that at all when determining our significant figures. So my final answer can only be written as 34%, because that number that we got after subtracting only has 2 significant figures, so therefore our answer can only have 2 significant figures. Now again, this is a pretty rare case. This doesn't happen a lot in science. A lot of times you can do, like I said at the beginning, you can look at the numbers that they give you in the problem and you can go, oh, this has 3, this has 3, my answer is going to have 3. Only when you have to switch in the middle from addition, subtraction to multiplication and division. That's the only time you have to worry about this. And again, it's not even that big of a deal, but especially with percent error, which is something you are expected to know, is that you do have to switch in the middle from your addition subtraction step to your division step. And so when you do that, you do have to take into account, oh, there's that intermediate number that we're using that we're going to apply when we do our division step. And then once you do that division step, oh, yep, we've only got 2 significant figures, so your final answer only has 2 significant figures.